Hello, good morning. Hello. Thank you for coming so early. I think this is the best time because it's not too warm. It's the beginning of the day. Um, I think last week, the homework has been done so well. I just want to mention one problem. Now, for some students, if you didn't obtain an A, it means that before you do the substitution, that means to put the value of A and the value of I into the equation to find B. Before you simplify, I don't think you should do the substitution. It's just my opinion. This is my opinion. Why? Now, part of our curriculum is to teach you, or you have to learn how to manipulate. Now, to manipulate symbols means this is algebra you learn. So this is very important, in my opinion, from this to this. These three steps are very important. So you learn that, oh, you can move the terms and then you can divide a coefficient. Is it fine? So afterwards, after you have expressed B in terms of A and I, and then you do the substitution instead of just putting the value of A and I, and in this case, 0, the dark 0, putting these matrices inside directly. That's not the best way. Is it fine? That's just one problem. One problem. Let's come back to today's lesson. The file can be downloaded in the Google Classroom. You can print it out. It's quite long today. This is for today's lesson. I think more than 10 pages, 12 pages. Now, last time we learned how to add, subtract, and then scalar multiply. And I asked you to guess what we should learn next. And I think you can guess it correctly. It's multiplication of matrices. Now, it's very rare we have to learn different multiplications. In the past, we never learned, oh, there are two kinds. Or you have to learn this addition and another addition. No. In the past, there is only one kind of addition. There is only one kind of multiplication. You don't have to learn it twice, but this time you have to, because the rules are completely different. Look at this multiplication of matrices. In this multiplication, you have two matrices, A and B. They're not random. They're not random. They have very specific size, the order of matrix. Now, A is of order M times P. And B is order P times M. Now, of course, M, N, and P can be different values, but if you pay attention, you should notice that, oh, the number of columns and the number of rows of these two matrices are equal. Now, only in this case, we can multiply A and B. And the outcome is a matrix C. Outcome, matrix C. A matrix C will be of order M times N. This is how you do it. This is how you do it. The first matrix, in this case, this illustration means A is 4 times 2. And B is 2 times 3. The outcome is 4 times 3. Outcome is a matrix 4 times 3. Then how to find out the 12 elements inside this new matrix? From this formula. This formula, you can write it out. It's quite long, but also you can shorten it using the summation notation. But anyway, you should understand that to obtain a certain element inside the outcome matrix, you have to use a certain row of A and a certain column of B. In this case, look at the red one, this element. This element is the first row and the second column. So I will take the first row of A and take the second column of B. And then I put them together. And this will be my C12. This one will be C12. This one will be the third row and the third column. So this one will be C33. Now it's difficult to just explain using the illustration. So I will explain more using examples. Now before that, please note that if the sizes don't match, that means if the number of columns is not equal to the number of rows, then A times B. This multiplication cannot be done. AB is undefined. Example. You are given 4 matrices, A, B, C, and D. They are different sizes. Can they multiply? We don't know. We will try. We'll try. So please find AB, BC, AC, and AD. So I put A, B together. A, 1, 4. B, 2, 3. Now, what do I get? First, the size. Look at the size. This one is 1 times 2. This one is 2 times 1. So I should expect that my outcome is 1 times 1. Okay? So my outcome will be a matrix of a single element. Now, how to get the single element? Very easy. There is only one row and one column. So I use this row and use this column. And I do multiplication and addition. That is 1 times 2 plus 4 times 3. That's one value. That's one value. So I used up all the numbers in this row and all the numbers inside the column, and then make this one single outcome, and that is 14. Okay, now pay attention. This outcome is not a number 14. It's not a scalar 14. It's a matrix 14. That's why you have to put 14 inside the bracket. Okay. For the second multiplication, B times C. B is 2 times 1. 2 by 1. B is 2 by 1. C is 2 by 2. In this case, they do not match, meaning the number of columns of B is not equal to the number of rows of C. Therefore, BC is undefined. Now, we don't even try. I think as soon as you find out, oh, the sizes, they don't match, then you do not proceed. Simply say this is undefined. Example C, A times C. Now, A times C, the sizes are 1 times 2, and this one is 2 times 2. In that case, I should expect the answer to be a 1 times 2 matrix. Okay, now how to obtain this 1 times 2? I'm gonna use the first row and the first column to obtain the first value. In this case, it's 1 times 2 plus 4 times negative 1. That's my first value. For my second value, I'm going to use the first row and the second column. So in this case, It's 1 times 1 plus 4 times 0. Okay? So after that, I've used all the numbers. And then I have the answer. You see a little calculation. The first value is -2. The second value is 1. And that is a 1 times 2. This is a 1 times 2 matrix. Last example. Last example. Now, how about A times D? Now, A 1, 4. This is D. Now, this is very similar. This is very similar. So the size, the order they match, then I will multiply. The first value, row 1, column. First value, 1 times -2 plus 4 times 0. Second value, 1, 4, 5, -1. In this case, 1 times 5 plus 4 times -1. In this case, I get -2, 1. Another matrix. Is it okay? Now, this definition of multiplication, obviously very difficult, very complicated. But I think if you try to follow and do some exercise, you will get, you will get it. So next page. Now this note we will discuss later. Next page, can we practice the classwork? P times Q, Q times P. Now, for each of the following pairs of matrices P and Q, find P multiply Q. Find Q multiply P. Now, when you are done, you let me know by raising your hands. Now, if you're stuck, let me know. Let me know. This is how you get the first value. The first value. This one. Okay. Now, I think that because you are new, even if you are very experienced in the future, I recommend that you will write this step. You will. Before you learn how to use the calculator. The calculator thing later on I'll explain, but right now you need to learn how to do it by hand. So you must write all the steps. Okay? For example, I'm taking this one, for example, suppose I'm going to calculate the last one. That's the second row and the second column. So I'm taking the second row and the second column. I'm using all four numbers. And you write it down. Don't try to figure it out in your head. Write it down. And then you calculate. This is the final answer. Is that okay? Now pay attention that you see P times Q in part B is a matrix. The outcome is a matrix because the size they match. But Q times P, no, no. A 2 by 3 and a 2 by 2, they do not match. That's why it's undefined. And this is very weird. It's, you see, this never happened in the traditional. The algebra with numbers, you don't have that. You can always multiply. You don't have to, oh, these two numbers, they cannot multiply. You can always multiply. But for matrix, not so much. Is that okay? Moving on. Moving on. This classwork, I'm giving you less steps. I think you can handle. Let me know if you're done. Let me know. Raise your hand in the Google Classroom if you're done. Now, it's never easy to really do it. It's never easy to really do it. You must find a way. You must find a way. Use two hands. Use two hands. Use the highlighter. Let's wait for one more minute. Now, if you're stuck, now look here and see how I get the number 7 here, this number 7. And 7 is from 5 plus 2. And how did I get 5 plus 2? That is the first row, the second column. That's just one example. One example. In the multiplication of matrix, that for this size is 3 times 2 and then 2 by 3. So that means you're getting 3 by 3. So in this case, you're doing a lot of multiplication and addition to get 9 numbers in total. Now you can imagine what the complexity is. It's not just, oh, you're getting one answer. It's not just that. It's addition, multiplication, and then do it 9 times. So it's okay to take it slow. Okay. Let me see if all have finished. Almost. Almost. Okay, we'll move on. We'll move on. Because you can still practice at home. Practice at home. The second example. I have 2 by 2 and 2 by 2, A and B. Multiply A to B and B to A. This multiplication, enough space first. So -1, 6 plus -3, -2. That's my first value. Okay. Now I always do it this order. I always do it this order. So I will do 1 times 6, 3 times -2. That's my second. And then I will do -1, -3, plus -3, 1. Then I'll have -1, -3, plus 3, 1. And then I'll get the answer. Okay. That's my first answer. Second answer. That's it. Huh? That's it. So in this case, I did 2 multiplication and you see the answer. You see the answer. You can do the same. Let me know when you're done. Okay, Emily, you must be quicker. Sophie must be quicker. Sophia also. Now practice. If you practice, you practice, you'll be better. Okay, you must do it faster. If not today, maybe tomorrow. You must do it faster. And also for these exercise, you see it's quite simple, right? These values are quite simple, but I'll write down everything. I'll write down this step. So later on you can check. It's also less likely that you make a mistake. Okay. Now, we have two examples just now. We explained two examples. And then I think we're ready to discuss how peculiar the multiplication is. The first thing. Now, from the first teaching example, you can see that there's something weird. Something weird. That is that you see A multiplies C and A multiply D. The answer is the same. You see? AC, AD, the answer is the same. And A is not 0, you see? A is 1, 4, not 0. But C and D are not equal. This is peculiar. Because usually in the past, when we did the multiplication of numbers, if you have A times X equal B times Y, sorry, A times X equal A times Y. And if A is not equal to 0, then you can divide. You can always get X and Y are equal. But in this case, in the matrix multiplication, you don't have that. A is something, A times C. C and D are not equal, but A times C equal A times D. Very strange. Very strange. So that is, today you are learning a new operation and also learn the algebra of this operation, is that it doesn't behave the same way. Although we call it multiplication, we say, oh, this is multiplication. In fact, inside the multiplication, you add. A lot of addition is inside the multiplication. So this so-called multiplication doesn't behave the same way the traditional multiplication behaves. So that's the first thing. Very, very strange. Very strange. So in the future, you must know that when you have AC equal AD, you mustn't assume C and D are equal. You mustn't. So that's the thing. The second thing comes from here, I guess. In this classwork, we practiced that H times K and K times H. I think it's quite obvious now. It's very strange that H times K and K times H are not equal. Sorry, this is K times H. So in the same, what do I call it? In the multiplication, even if you can multiply, in this case, 2 by 2, you can multiply it either way. You can multiply HK, KH, either way. But the outcome, although both of them are 2 by 2, they're not the same. In fact, not single one number is the same. You see? And in this case, it's even more different. You see, H and K, K and H. Hey, what am I doing? Oh, sorry. I think it's this way. This way. This is HK, this is KH. This is HK is K. In this case, HK is 2 by 2. KH is 3 by 3. In other words, it can be, the outcome can be so different that even the order of the matrices are not equal. So this is not equal. H times K times H not equal. Sometimes the size are not even equal. They can't even be to be put together to discuss. So this is something very strange about matrix multiplication, is that, what do we call this? It doesn't commute. It doesn't commute, meaning you cannot swap them. But for more normal multiplication, you can always swap them. It doesn't commute. Commutative property doesn't hold. It does not commute. Okay. Second, the last thing from the second example. Something strange about this multiplication, please notice. Something strange about this multiplication is that A is not 0. B is not 0. But A times B is 0. Very strange. A is not 0. B is not 0. But A times B can be 0. Now this 0, dog 0, dog 0. This could never happen with the number multiplication, scalar multiplication. Never happen. We always say the 0 principle, that if x times y is 0, then x is 0 or y is 0. One of them must be 0, but in this case, no. You see this one? That's one example. The classwork is another example. You see, this is not 0. It has 1. It has a lot of 0 in it, but the matrix is not 0 matrix. Now this also not a 0 matrix, but this one is a 0 matrix. Now, of course, if you swap them, it's not 0 again, because h times k is not equal to k times h. So one of them is 0 and the other one is not. Okay? Isn't it weird? That's why you need to learn a whole new set of skills in order to manage the algebra of matrices. Let's move on. The next example is to learn something. Also, it's multiplication. We practice multiplication, but we also learn something. So to get these values, this so 1, -1, 1, -1, 1, -1. Very lazy. I'll do that. 2, 0, 2, 0, 2, 0. Okay, and then I get my answer. It's 8. Okay. Another multiplication, B and C. Huh? You shouldn't have this. You shouldn't have this. It's only one column. One column. So this one is 0, 2. Okay. Sorry, I messed up with the size. It shouldn't have the second column. It's just one column. Okay. Now let's do A, B, and C. So you use the result of A, B, and then multiply C. So the result of A, B. 8, -6, 1, 10, 0, 6. Right? Let's do it. 8, -2, plus 10 times 1. -6, -2, plus 0. 1 times -2, plus 6. And that is right. Now using the result of BC, which is 0, 2, multiply A again. Multiply A again. So in this case, 5, 0, plus -3, 2. 0, plus 4, 2. Am I right? Why is the answer not the same? Zero, 2. And 0 plus 2 times 2. And I get -6, 8. Eh? -4, 4. Because I'm expecting that the answer should be the same. Let me see. -4. For part A, the second row, -4. -4. Oh, this one, -4. Sorry. Yes, -4. Not 0, -4. So this one is -4. So this is -4, -2. So that's why it's not -2, 1. -4, 1. Right? And that is 8. Yes. You see, you can't make one mistake. You cannot. You can't afford to make one. Even I just wrote down all the additions, but still. Anyway, now it's a simple question. You do multiplication and then you do multiplication again. And then we learn from this multiplication. We learn. How do we learn? We learn that for this result and this result, A and B. Now we multiply AB and then we multiply C. The outcome is the same as we multiply BC first and then multiply A. Now pay attention that I just changed the order of the multiplication, but I did not swap them. I did not put A at the last. The position ABC, they still follow the same order. A, B, C. This one, A, B, C. It's just that I will sort out BC first and then multiply A. Where in this case, I sort out AB and then multiply C. Now this is very common in normal multiplication. If you have 2 times 3 times 10, and then 2 times 3 times 10, it doesn't matter how you multiply, as long as you multiply. So in normal multiplication, this is very common. And this is also true. Now, we hardly can find anything that's normal with this multiplication, but this is still true. If you solve AB and then sort BC, the outcome is the same. So we learned that A, B, C equal A, B, C. So in the future, when you see this, you don't even have to write the multiplication. You don't even have to write the bracket. It's just A, B, C. Okay? You just write that and we know. And it doesn't matter how I multiply. Doesn't matter. Now pay attention that you cannot swap them. You cannot say, oh, let's do B, C first and then do A. No. Cannot do that. Cannot swap. You can group them. So that's the thing. Can group them. Can you do the practice, please? And let me know when you're done. Let me know when you're done. Let me know. Okay. Now, this one, the quick practice, it's exactly the same as the example, but it provides more evidence. It's not a proof. It's just more evidence that you can associate PQR. You can do it any way you want, as long as you do not change the sequence. Okay? And also along the way, we'll practice multiplication. Practice. Now, before we move on to the next part, we learn this is the basic of multiplication, basics. Before we move on to the properties, learning properties is like a higher level of algebra. It's not just learn how to do it. You learn how to simplify, how to do it faster. But before we move there, and I want you to look at this. It's not on your notes, but I will show you on my screen. It's not on your notes. I didn't print it out. Look here. I just put it on my notes, but it's not on your notes. You just look at it and you will understand. I hope you understand. It's also here. I can show you here as well. That there's a table, another table, and another table. I hope that using this example will show you that, oh, the multiplication, although it's very weird, the definition itself is very weird. It should make some sense. It should make some sense. Look at the first table. Apple, $5 per kg. Banana, $4 per piece. And cherry, $8 per pound. I think you can understand what it means. Right? And we see this all the time. In real life, we see this all the time. You see this $5, $4, and $8. They are not even of the same kind of rate. They are of different. One is per kg, one is per piece, and one is per pound. Okay? And then there are three people, Miss Chan, Miss Lee, Mr. Wong, right? And then you can see another table. I think you can understand, it makes sense of it, although I don't describe it. But when you look at it, you should know what does that mean. Now, in the first column, Ms. Chen, 2 kg of apple, 6 pieces of banana, 0 pounds cherry. Ms. Lee, 1 kg apple, 10 pieces banana, cherry, 0.5 pounds. And Mr. Wong, 0 kg, 0 pieces, 2 pounds. Okay. Now, if you look in the past, you call this a table. This is a table, this is a table. Now, today you can call it matrix 1, matrix 2. Is that okay? Now, let's look at what if we multiply them? What do you get? Now, because I need to annotate, so I changed to this. No, it's the same. It's the same. Now, what if I multiply this row? This row. This row to this column. Multiply. I will get this value for Miss Chen. This value. What does that mean? 5 times 2 plus 4 times 6 plus 8 times 0. This is the normal, what we call the, not the normal, the new multiplication we learn, right? Okay. And we can also use the first row, multiply the second column. What does that mean? I get the second value, right? I get the second value. So what does that mean? 5 times 1, 4 times 10, and then 8 times 0.5. And what does that mean if I do the third multiplication? Question. Do the numbers mean something? Do they mean something? Hey, do they mean something?
Yeah, like their sum is the total value of the amount that they have to pay.
Yes, I think you can make sense of it, right? Now, from this example, I hope you know that. Just to know that, bear in your mind that the multiplication of matrix does not come from our imagination. It really comes from real life. Now, in real life, we do this multiplication all the time. That's why this multiplication is invented in matrix, and it has a lot of applications. This is just one of them, and this is very, very basic. Very basic. In the future, you will learn how to use matrix to solve problems. Is that okay? So this is not imaginary. This whole thing, very complicated, but not ungrounded. It's based on something. It's based on something. Now, let's come back to the notes. Now, it's like the last lesson. After we learn the operations, we learn the properties. The first property. The first property is called the associative property. I just explained. The proof is in the textbook, but we don't want to go into that. It's quite complicated. The proof, because you need to verify if every outcome is the same. It's not just one number, because the outcome is a matrix. So you have to verify if every single one element, they are equal. In fact, they're equal. Okay, and this property is called associative property. It's also true in numbers. In numbers, A, B, C equal A, B, C. So in the future, you don't have to write the bracket. B and C. Now these two, we don't have proof and we don't have example, but I think you will use it. You will use it. Bear in mind that they are true. In numbers, you also have them. Obviously, they are true. Okay, but you pay attention, after the expansion, I did not change the position of A and B. It's still A in front, B second, A in front, C second. I do not swap them. I just expand them. That's why we have the second expansion. This one I do not swap them. A, C, B, C. Okay. Now, how about subtraction? Subtraction, you also have the same expansion. You can write it down. It's not in the textbook, but you can write it down. A times B minus C for matrix. It's AB minus AC. As long as you don't swap them. And B minus C times A is B, sorry, 8. Let's be consistent. A minus B times C equal AC minus BC. You can expand. This may be the most mysterious, but trust me, it's the same. It's the same. The last one, the fourth one. The fourth one is a mixture of scalar multiplication and matrix multiplication. So that means that if you have some coefficients, you can put them out and do the coefficients multiplication first. This is a simple multiplication with numbers, scalar multiplication. And then instead of doing the matrix multiplication last, you do it first. This is matrix multiplication. And then you do one last multiplication. Basically, you have numbers, matrix. You do the numbers, and then you do the matrix, and then you put them together. Instead of, doing this and put it together. You know what I mean? It's usually simpler this way. Lambda and mu. Lambda and mu are scalars. Okay? I'll show you one example. For example, 2 times 1, 2, 3, 4 times 3 times 6, 7, 8, 9. That means you put 2 times 3 first, that's 6. And then you put 1, 2, 3, 4, and then 6, 7, 8, 9. You do this first, and then you multiply. That's 4. 4 properties explained. Now, pay attention, I didn't swap A and B. A is in front, then B. A is in front, then B. I do not swap them. I changed the order of the scalars. I put scalars first. I can swap scalars, but I do not swap the matrix. Next, A times I equal I times A equal A. Now here I is the identity matrix. Now this one, we don't prove it, but I'll show you evidence. Evidence. You see, A is A, B, C, D matrix. I is the diagonal matrix, you see, identity matrix. Diagonals are 0, and then, diagonals are 1, and other places are 0. So this is a 2 by 2. This is 2 by 2. So what is A times I? A times I. A plus 0, B plus 0, 0 plus C, 0 plus D. You see? It's A, B, C, D. It really is. A times I really is equal to A, B, C, D again. Now, how about I times A? I times A, it's A plus 0, 0 plus B, C plus 0, 0 plus D. A, B, C, D. Evidence. Now you can say, it's a proof because A, B, C, D can be different, right? But it only is an evidence because this is only the 2 by 2 case. There are other matrices. There are other sizes. So that is one evidence, let's say. Is that okay? Now, normally we will say that, A times B is not equal to B times A. But in this case, A times I and I times A are the same. Sometimes they are equal. You cannot rule out, oh, just because you swap them, the outcome is not, they're not equal. Not always. Not always. In rare cases, A times B equal B times A. In this case, I. Another piece of evidence of different size. You see, B is this 1, 2, 3, 4, 5, 6. I is identity matrix. Let's verify if B times I equal B. Right? 1, 0, 0. 4, 0, 0. And then 0, 2, 0, 0, 5, 0. And that's 1, 0, 0, 3, 0, 0, 6. It really is. You see? This is another evidence, another piece of evidence. You think B is not square matrix? Some people say, oh, it has to be a square. It doesn't have to. You see? B times I is B times I is B. B times I is B. Now, how about I times B in this case? Now here, because the size don't match, then I times B is undefined. Oh, you may say, oh, Ms. Chen, then I times B is not equal to B times I then. Now you have to go back and look at how careful our textbooks are. It says right there in the first sentence that A, B, C are matrices such that the following operations of matrix are defined. Meaning that if it's defined, they're equal. If it's undefined, then they're not equal. In the first evidence, you see that they are both defined, right? AI and IA are both defined. But then they're equal. For the second one, BI is defined. BI is still equal B. But IB is not defined. In this case, if it's not defined, they're not equal. So our textbook is very careful when stating something like that. When saying, oh, IA equal AI. Yes, they are equal if they are defined. If they're not defined, okay? So in the future, when you have anything times an identity matrix, that's equal to that matrix. Last one. A0 and 0A. Evidence. 0 is the dark 0. So I'll use the 2 by 2, for example. So A0, you can see A0. The calculation can be very quick. So that's 0, 0, 0, 0. Right? If you put it in front, it's still the same. I do 4 numbers separately, but outcome still dark 0. So you can believe me. You can believe. I think this one is more obvious. It's anything times 0. Still 0, right? Now, how about different size? You can this different size. This is 0 matrix, right? And this is different size. So this one is 0. That's the first value. The second value also 0. Right? And the third value is 0. And the last value is 0. So even if it's a different size, it's still 0. The outcome is 0. It's a 2 by 2 0. It's a different 0. It's a different 0, but still 0. Okay. This one, it's 1 by 2, 2 by 1. So the answer is 1. 0 plus 0. That's 1 by 1 matrix 0. Still 0. Is that okay? Both of them are 0. Now, usually we will discuss the square matrix in our practice. we do more with the square matrix, but with non-square matrices, yes, still, as long as they are defined, that's the outcome. Is that okay? Any questions with the properties? Any questions? Then we move on. We will solve the following problems using the properties. Please note that since the identity matrix acts very similarly as the number 1 acts in numbers. Why? Because you see, AI equal IA equal A. It means I does not change the outcome of the multiplication. That's very similar to 1. Now A times 1 equal 1 times A equal A. So we, for convenience, we will define the power of square matrix. Otherwise, it cannot multiply. That is A square. We define A square. A square is A times A. A cube is A squared times A. AN is A times AN minus 1, basically. That's the power of square matrix. And also we have this definition, A to the power 0 is I. It's just for convenience. Is that okay? Because in the numbers, we have A to the power 0 equal 1. Here we have A to the power 0 equal 9. Is that okay? Now, in particular, for very special matrices, I is identity matrix. Now, you know that I times I equal I, right? Because I times A equal A. So A can be I. So I times I equal I. So I square equal I cube also equal I. In fact, I to the power n also equal I. It does not change. Does not change. Now 0 to the power n equals 0, dark 0. Okay. So we do, there are special matrices. From the first lesson, we know that there's special matrices. Now I acts like 1, 0 matrix acts like 0, but not exactly, because there are different zeros and different i's. Okay, think further. Now we are now discussing the algebra. So you must think whether or not these identities are still true if A and B are matrices. Because in the past, these identities are all true for any number, including complex number. Are these still true? The first one. No, it's not true anymore. Not true anymore. So left-hand side is A plus B squared. So we can say that this is not true anymore. Usually it's wrong. They're not equal. Because A plus B squared, it's still equal A plus B times A plus B by definition. But after the expansion, you will get AA plus BA plus AB plus BB. So to simplify to the most, you can say this is A squared plus BA plus AB plus, not BC, BB, BB. So that's B squared. To the simplest, you can say, oh, this is still equal because the expansion is still allowed. Now, what we call that expansion, that's called a distributive law, right? The distributive property. You can still distribute. It's just that you cannot say this is 2AB anymore because BA plus AB is not 2AB. Okay? This is still true. This is not true anymore. For the second one. True or false? Sophia, yeah. True or false?
False.
What is it really equal to? Sophia, what is it really equal to?
The because it should be 1AB and 1BA.
So it's a square minus BA minus AB plus B squared. This is still true. It's just cannot be negative to AB, correct? Now this one, true or false? Cherry? Cherry? Cherry is absent? I saw her. Cherry?
Oh, yes, I'm here, sorry.
So this one, true or false? Did you fall asleep?
No, I didn't false. Is it false?
False. So what is it really equal to? A plus B and minus B. What is it really equal to?
AA plus AB minus AB minus BB.
I think it's minus AB plus BA.
Okay.
AA minus AB plus BA and minus BB. You see, this is plus BA. You do not swap them. Do you see that? Now, in the past, we say, oh, AB and B are equal, so these two, they cancel each other out, but now they don't. They don't. You still have AB and BA. Okay? Now, part D, this one, is it still true? I think no. Not anymore. Because this one, if you want to do the expansion, it should be A, B, A, B, A, B, A, B. A lot of ABs. Now, because you cannot swap them, AB and BA are not the same. So now you cannot swap them. That's the most expansion you can do. You cannot simplify anymore because you cannot swap. I think most of the problem with the identities is that in the past, we can always do the, what do you call it? Commutative. In the past, it's always commute, so you can swap them. Now you cannot swap. This is what you can do. You can still expand, but you cannot put them together. You cannot put A together and B together separately. You cannot. Last one, true or false? Cassandra?
Is it true?
Yes, it's true. This one is true. This one, because you see that A plus I square is A square plus AI plus IA plus I square. The expansion is still true. And with AIIA, they are the same. It's A square plus AI plus AI. I square. Now, IA and AI are equal. So you can swap them for this one. And that is A square plus 2AI plus I square. That's correct. In fact, you can even simplify it more because A square, AI is A. So you just write 2A. And I square is I. So you just write I. So it can be further simplified to this. This is a true identity. Very rare, but still true. So you must really be on alert. Sometimes these can be used, sometimes cannot be used. You must know yourself. Okay. Example 11. This is a simple example. I have this code for you so you can try to input the program. This program only covers the case 3 by 3. It's 3 by 3 times 3 by 3. You watch the video and you input the program in your calculator, and then you can do it quicker. But anyway, during the lesson, this is how you do it. This is how you do square. Second one. Okay. I'll do it quicker this way. If you're doing all by yourself, it's more difficult. So this one is okay. You use the calculator, okay? Now afterwards, I'll use a squared to calculate a cube. And there is no better way to do it. You have to do it one by one. You cannot do it, oh, let's do it cubic direct. You cannot do cubic directly. You must do square and then cubic. So the outcome, I'll just write it down. Okay, I'll show you the answer then. I'll show you the answer then. So you do it and I'll show you the answer. I find out the answer from the textbook. Me doing it is too slow. This question, I think. Okay, this is the answer. A squared is this answer. Let me see if I'm correct. Yes, a squared is this answer. The a cube is this answer. Okay, so that's the first example. With the classwork, when you are done, let me know. Let me know. Oh, there's no. Okay, there's no. You don't need to do it. You don't need to do it. It's simple. The second example, it's more structured. So I'll show you what to do. First, you simplify this. This is algebra, you know. This is algebra. There's no substitution. This just simplify. This is algebra. How to simplify? You just do this. P minus 2IP minus PI minus 2II. That's the expansion. Remember the order, cannot swap them. And then you do P squared minus 2P minus P minus 2I. And then you take P squared minus 3P minus 2I. I think that's proven. Plus 2I, plus. So this is to use the property. I use the distributive property. I use the other properties. So to simplify. The second, can you show that this is 0? 0 means the dark 0. Is this matrix equal to the dark matrix? And that is, there's no mystery here. You just substitute and see if it does, if it equals 0. And it is. It is. Let's first do the square. Let's first do the square. 2, 0, 2, 0, 3, 1, 3, 1. Okay, and then I get 4, 0, 9, 1. Okay, so 4, 0, 9, 1. I put it in. So m squared plus minus 3m plus 2I. That is 4, 0, 9, 1. This is 6, 9, 0, 3. Right? And then you get 0, 0, 0, 0. And it is equal to dark 0. It's equal to dark 0. And when you write dark 0, you write like that. Finally, finally. Now, perhaps when you read it, you don't know what to do, but this is another piece of evidence, basically. Now, since we have, if we have this condition, do we have this conclusion? I think just now I explained, just because two matrices multiply is equal to 0 doesn't mean one of them must be 0. It's correct with numbers, but not correct with matrices. So how do you explain? You can use part B to explain, because this is a perfect example. This is a perfect example. For B, we already know that when P equal to this very specific example, 2, 3, 0, 1. So this one, because this P is equal to M, this is M. So P minus 2I is M minus 2I. P minus I is M minus I. And this can be equal to M squared minus 3M plus 2I. This is from part A. By part A, we already proved that this expansion is equal to this. Okay. And by part B, we already know that this is 0. 0 matrix by part B. Therefore, we have an example of two matrices. Their multiplication is 0, but these two are not 0. M is not equal to 2I, and M is not equal to I. You see what M is? This one. This one is not equal to 2I, because 2I is this one. This is 2I. I is this one. Now M and 2I, M and I, they're not equal, but M minus 2I and M minus I, their multiplication is a 0 matrix. Therefore, we cannot make such a conclusion. Just because two matrices multiply equal to 0 doesn't mean one of them is 0. Is that okay? Now you do this and you let me know when you're done. Quickly, quickly. Let me know, let me know. Okay. Most are finished. Now it's not that, oh, if you try to understand it, this practice and the example is just trying to show you that, oh, something we already explained before. It's the same thing that a zero matrix can be obtained by two non-zero matrices. I think when you just gain more and more experience on that. If you find these questions are a little bit too weird, try to get used to it. I promise you get better next time. You will get better, but don't give up. Don't give up. The homework is gonna be very basic. Don't give up. I think that's it. We have a final example, but I'll show you next time. A lot of you can even read it yourself. I think you can. I think you can. So I'll see you next Tuesday. Cherry, you can stay. Others you can leave. Cherry, you stay.